do it. In this lab, we are going to go over background for data preprocessing and feature extraction. You will learn various techniques such as stemming, removing stop words, and feature extraction, such as back of words, TF-IDF, and parts of speech tagging. To accomplish this lab, you need a computer with Python version 3.7 or later installed, as well as a Python IDE. For your first task, you should implement a function that will collect news articles using the Guardian API with news articles from different topics. You can use software packages such as News Please to collect and curate the news articles, and you can also use the Guardian API found at this link. You can also use the provided URLs in the Guardian metadata JSON-L file to extract the content of web pages. So let's look at the solution. Here is the solution. If we go to the main of the code, we see that we have a web crawler and it's crawling the API content for the news articles, and it's getting news articles from 2016 to 2018. It will start crawling the file that we provided to store all of the content of the news articles into our project. So if we go to the start crawling function, we notice that we're creating a directory called Guardian2. We've already run this code, so you see the directory Guardian2 here, and each news article is stored into a separate file within the Guardian2 directory. So now the next task is to apply text processing to these news articles. So in this second task, you should implement a function that will stem all of the words in a given text file. You can use a package such as nltk.stem.porter to accomplish this task. So stemming means to reduce a word into its word root. So for example, stem, stemming, and stemmed all have the root of stem, so they all are reduced to the word stem. So a sample solution for this task here is showing you that we are importing the porter stemmer from the nltk.stem.porter package, and then we give the sample sentence as input text, and then we are splitting each word in the sample sentence, and then we iterate through each word to stem each word using the porter stemmer. So if we run this code, we see the words after stemming. So notice Salvador's turned into Salvador, and citizens turned into citizen, pudding turned into put. So this module shows you how to stem words in a corpus. Our next task is to implement a function that will remove all stop words in a given text file. You can use a software package such as NLTK Tokenize to accomplish this. Stop words are words that do not add to the meaning of a sentence. So for example, some stop words could be a, an, the, and, or, but, or, no, nor. So here's a sample solution. So if we go to task3.py, we see a sample solution. We are importing the NLTK corpus stop words module, and then once we import this package, we see that we are importing stop words in English. We give this sample sentence as input text, and then we're filtering out stop words in this sample sentence. So we first split the sentence into separate words, and then we say if the word is not a stop word, then we add it to a filtered words array, but if it is a stop word, then it won't be added to the array. So if we run this task, we notice that before the stop words removal, it had some stop words like a and to, but then after removing the stop words, we notice that these stop words are no longer part of the array. Our next task is to implement a function that assigns part-of-speech tags to every word in a given text file. You can use a software package such as NLTK pos_tag. For example, parts-of-speech tags for the sentence, "My name is Jocelyn." My would have the tag of PRP, which means proper pronoun, singular. Name would be the singular noun. Is would be a third person verb, and Jocelyn would be a proper noun. So here's a sample solution for the task. We go to task 4, we notice that we import pos tag from NLTK. This is to get parts of speech tags, and we also import word tokenize, and this is to tokenize or split the sample sentence into separate words. So if we run this task, we notice that we get parts of speech tags for the sentence. So US would be a proper noun, and Senate would also be considered a proper noun. Has would be a third person verb, etc. So this shows you how to generate parts of speech tags for sample corpuses. Your next task is to implement a function that will find named entities in a given text file. You can use a software package like NLTK tag, Stanford NER tagger, to accomplish this task. For example, the named entities for this sentence, "John lives in New York," would be B per O B lock I lock. This uses IOB notation, which means inside, outside, and beginning. So John is a beginning person, and then the O means it's outside, which means it's not a named entity. New would be the beginning location, and York would be the inside location. So here's a sample solution for this task. So here we notice that we're using the Stanford NER tagger to get the NER tags for English, and then we provided the sample sentence to get the NER tags, and we extract the NER tags for each word. So here in the extract NER function, we are splitting the words of the sentence, and then we're getting NER tags for each word. So here we're just getting the tags for each word, and as long as that word is not a null string, then we extract the NER tags. So if we run it, we see the NER tags being extracted. So El Salvador is a location, Alexandra Hills is a person, Minister of is not considered a named entity, etc. The next task is to implement a function that will extract bag of words and TF-IDF features in a given text corpus. You can use a software package such as sklearn feature extraction.txt. So let's look at a sample solution. Here is a sample solution. Count vectorizer is used to get bag of words, and TF-IDF transformer is used for TF-IDF calculation. So here's our input corpus. We're just providing sample text to show you how this works, and we are saving each of these count vectorizers and TF-IDF transformers to a variable, and we print out the features. So here you notice the bag of word features, so it's providing the frequency that each word occurs in the corpus. So for example, extraction occurs once, or it occurs twice, and embedding occurs once. And TF-IDF features provides the time frequency, inverse document frequency for each of the words, and you can see the calculations here. So this concludes Lab 1.